Welcome to today's session of fluid inclusions in minerals. We have been discussing about the application of fluid inclusion microthermometric data to ore forming environment to understand the origin and the path of evolution that the ore fluid actually passed through during different identifiable stages of mineralization in any mineralizing system where a hydrothermal fluid is involved. As we have said, this literature on the hydrothermal ore deposits and fluid inclusions, especially in different types of hydrothermal systems, a wide spectrum of hydrothermal systems, are actually too vast. We will just take some examples and then go through the fluid inclusion characteristics, the rationale that is developed in linking the entrapment of different generations of fluid inclusions in different host minerals in accordance with the established or identified stages of mineralization in a particular deposit. It could be a single episode of fluid activity which could have given rise to mineralization in different locales, or it could be multiple stages of hydrothermal activity with multiple sources which would have given rise to mineralization of metals in different locales, as has been exemplified in some of the cases like the volcanogenic massive sulfide deposits, the and in cases like the one which was the Indian example which was described. So, we will continue with one important one important class of hydrothermal deposit, that is known as the IOCG deposits, the iron oxide copper gold deposit, and this particular deposit owes its origin to the discovery of the giant Olympic Dam deposit in Eastern Australia, in southeastern Australia, in the Gawler Craton. And since then there has been, because this is the very first time that rich mineralization of copper, uranium and gold was discovered in a zone, brecciated zone in a granite of continental interior mostly during the middle Proterozoic time, within about 1600 million years to 1350 or 1400 million years time. And this discovery of this deposit was a major breakthrough, and it gave rise to many further exploration programs in other continents. And over the last 32 years, or about 3 decades of discovery of this particular deposit, there are many more such deposits occurrences reported from other parts of the world, which are also named as iron oxide copper gold deposits based on the association. But we would confine ourselves when it comes to the fluid characteristics and the evolution of the fluid, or the inferred path of evolution of the fluid, by taking the Olympic Dam giant deposit, or rather the IOCG province in South Australia in the Gawler Craton. And so, let us just have a look. Even though it is not intended to discuss the genetic aspects in detail about this particular deposit, but we will try to see how the ideas have evolved, or what was the original idea regarding the origin of the hydrothermal fluid and its evolution in this particular classic deposit. If we look at this diagram taken from the book of John Ridley and the ore deposit geology, where a cross section of this Olympic Dam deposit in the Gawler Craton is shown, and the very peculiarity of this particular deposit, that it is covered by younger sediments, and this constitutes the Proterozoic rock ensemble constituting of the Roxby down granite and a zone of brecciated granite, and the mineralization is confined to this brecciated zone, where we also do have representative of the contemporaneous Gawler range volcanics. And what we could see here, that this represent the particular cross section of a mineralization zone, where there is a depth wise variation in the mineral assemblage, at depth you get mainly pyrite dominated, then it gives rise to chalcopyrite, bornite, chalcocite, cohalite type of sulfide minerals, and also associated with rich gold and pitchblende mineralization. And this is being interpreted in a way that the sulfidation state decreases towards the from bottom to top. And the interesting facts about this deposit is that mineralization is mostly within the Brixia complex. So, by later stages of cementing within the Brixia, or as later cross cutting veins. And one of the important aspect of this deposit is that the host there is no abundant proper host mineral like quartz in all the different stages of mineralization to extensively study the fluid inclusion characteristics, but there are other associated gangue minerals like fluorite and barite, which do help in constraining the fluid characteristics in infer different stages of mineralization. If we look at the fluid inclusion characteristics, which was first studied by Oreskes and Einody and was published in 1992. And what is interesting is that these Brixia do have initially magnetite as well as hematite, and the magnetite hematite coating on this Brixia zone, which could be the basement sedimentary rock or the granite material itself. Then there are some alterations which are also observed, like chloritic or sericitic alteration, which does indicate that within these stages during which this iron oxide deposited precipitated, it must have happened in some kind of reactions which would have given rise to acidic alteration of the material there. So, the first one to deduce a kind of fluid evolution path of fluid evolution was way back in 1992, and from this mineralization what Oreskes and Einody started. So, they also interpreted in terms of a early magnetite, siderite, pyrite type of mineralization, which was later imprinted by hematite, sulfide, gold and uranium mineralization from low temperature fluid. So, the interpretation from extensive fluid inclusion studies present in quartz, fluorite and barite from the different stages, like is shown from the early pyrite stage, pyrite magnetite stage, which could be more akin to kind of a skarn kind of stage, and then later on giving rise to a sulfide stage, which have been interpreted in differently by different authors, as we see later. This kind of interpretation is absolutely mine, and the initial interpretation made by the authors are that there was mixing of two different types of fluids, because they did see that one component of the fluid represented low saline, low temperature oxidized fluid, and the other one is a moderately high temperature going up to 400 degrees centigrade, which they thought could be possibly from a magmatic fluid. And the mixing which was deciphered was that this low temperature oxidized fluid carried the copper and maybe uranium, and on its mixing with this moderate temperature fluid which contained the iron. So, the iron underwent a kind of coupled oxidation reduction reaction, giving rise to deposition of iron oxide in the form of hematite, and liberated such kind of reactions, which also we saw in the case of the Malanskan deposit fluid mixing. Similar kind of situation was deciphered, but here giving rise to mostly hematite. So, the fluid which was a relatively moderately saline and a high temperature fluid was speculated to be of a magmatic derivation, and the low temperature fluid could have its origin source from some kind of a basinal fluid, or could be seawater, or a basinal fluid, or could be groundwater. That's what was deciphered, because this work was purely based on the fluid inclusion assemblages, fluid inclusion microthermometric data, without much of isotopic or any in situ microanalytical data on the fluid inclusions. So, later on in 1995, Heinz et al. Also they deciphered three ore associations. The first one is the magnetite, hematite, siderite, pyrite, chalcopyrite and uraninite with chlorite and sericite. And the second stage was hematite dominant, chalcocite and bornite, where we see that the the sulfides are basically giving rise to a more chalcocite bornite kind of mineralogy, with pitch blende, and the latest stage was the hematite, quartz and barite, which was kind of non-sulfide bearing stages. So, this stage 2 was the most important mineralization event, and they did combine their result of fluid inclusion study with water rock simulation of fluid rock interaction by taking hypothetical meteoric water and then titrating with the mineralogy of the Roxby Downs granite, and in similar such calculations they also deciphered that the conclusion about the fluid mixing, which was earlier deciphered by Einaudi and Rodriguez in their work, was corroborated, was supported, and also it was concluded that this iron oxide deposition along with sulphide was mainly ascribed to a coupled oxidation reduction reaction like the one which was discussed before. And this stage 1 to 3 or the results of concomitant mixing that resulted in the zoning and also the brecciation, they ascribed the brecciation to also concomitant fluid mixing and boiling phenomena, although this remains a little bit of a conjectural issue as to how this brecciation could have been brought about, but according to Heinz et al. 1995, this was a more of a concomitant mixing and zoning of the way the zoning in the mineralized different sulphide associations has been shown. Now, later on Davidson et al. In 2007, they studied a locality which is just within the same IOCG province of Eastern Australia, the Oak Dam deposit, which is little east southeast of the Olympic Dam deposit, and they interpreted that this brecciation was early with and the total 4 stages of mineralization. One was the filling by hematite goethite, and then magnetite stage with magnetite, apatite and quartz, then hematite, goethite, pyrite, monazite, chlorite, and then the copper uranium gold stage with the pitch blende and carolite and covellite and carolite deposition, and they deciphered from their fluid inclusion studies that the stage 3, which is basically the stage in which much of monazite, hematite, goethite and monazite was precipitated, was a moderately saline, low temperature 170 to 190 degrees centigrade, which also indicated boiling. And they deciphered that copper uranium mineralization that resulted from a stratified hydrothermal system like what we observe in a Salton Sea geothermal system. This copper, iron and sulfur. So, here as far as the different propositions are concerned, the first model of mixing ascribed most of the copper and uranium to have come from the low temperature oxidized fluid and the high temperature fluid contributing to iron, and this view sometimes get changed. In this case, the copper, iron and sulfur is both copper, iron and sulfur are deciphered to have been sourced from deep circulating fluid, which are essentially a deep evolving reservoir which underwent boiling and cooling and mixing with steam heated uranium rich saline groundwater. So, the here the other component was deciphered to be a steam heated and uranium rich oxidized fluid, because in order to have uranium, the fluid uranium dissolved, it has to be a oxidized fluid so that it could carry uranium, and the fluid mixing has to be invoked in order to get the uranium deposited in the form of +4 insoluble oxide form. Now, this recent work from Sklezel et al. 2018, they studied from they also studied the IOCG from the this prominent hill iron oxide copper gold deposit as shown here. So, this is a map of the IOCG province in southern Australia. This is the this 2 is from on Olympic Dam. The number 7 is the Oak Dam, which is just described as the work by Davidson et al. 2007, and one can see that the total ensemble here. This is the on the green is the Gawler range volcanics, and the red ones are the later intrusives like the granite which is described as occurring within the Olympic Dam deposit. There are earlier phases of granite, and the whole ensemble is shown here, which constitute the iron oxide copper gold mineralized province. Now, coming to the prominent hill IOCG, the plan, the map which is shown here, here it is quite clear that what is actually we are seeing from the magnetite rich zone is essentially could be thought of as a earlier skarn type of mineralization zone with some amount of pyrite, and then later on the sequence actually was in the order of this creation of this magnetite rich breccia, and then later on this breccia fillings and the deposition of the sulfides in different stages. So, here is the massive magnetite skarn, and this is the sedimentary horizon, the breccia, and the these are the calcilicate green species rocks here, and there are as usual there are some structural complexities which helped in the hydrothermal fluid that circulated, and these zones are the intense hematite quartz zones, and these are the zones which are represented by the polymictic pebble to cobalt breccia with minor lithic dacite, and sandstone with this sandstone intervals, and these are the salomorane mudstone. So, this entire sequence shows the Proterozoic basement sediment along with the magmatic units, the volcanoplutonic unit, and this is represented by the Gawler volcanics. So, in this work the authors they deciphered the two stages of mineralization. The stage 1 is the pyrite chalcopyrite moderately reduced fluid hosted to be subeconomic. These are all the post magnetite one, which is the skarn phase, and the stage 2 economic sulfide stage from hypogean oxidized fluid source from the paleo surface. And here also the fluid inclusion was done from different types of host, and as I have said that in the recent literature on any of such mineralizing systems, what we see is that we get to see some good quality, good resolution fluid inclusion images, and also in addition to that the fluid inclusion microthermometric data are actually supplemented with some good analytical data, including the in situ non-destructive analytical data as well as isotopic data. So, the conclusions that are derived is actually by combining or collating, synthesizing all information which is obtained from different sources. So, confining or restricting ourselves to the fluid inclusion characteristics and the fluid inclusion data, microthermometric data that was synthesized by these authors. So, they studied the magnetite quartz vein, the syn post sulfide and the post sulfide two veins, where they found the inclusion types were the aqueous biphase inclusions with variable liquid vapor ratio, and the aqueous liquid plus vapor plus halite kind of inclusions. Here there are some kind of inclusions which contain some red minerals, maybe it could be some iron oxide or sometimes some opaques, and these represent the most saline of the fluid components, which component multiple consisting or including some multiple daughter phases along with halite. So, in this case this the liquid vapor plus solid plus more than one solid kind of inclusions which are obtained from the magnetite quartz vein, they have a homogenization range of 275 to 475, and the inclusions which are containing a single solid phase or halite and liquid vapor inclusions had temperature of homogenization from 200 to 350 degrees Celsius, and the liquid vapor homogenization liquid vapor inclusions which are present in the quartz in the infilling of the breccia, and they represented in the both the sulfide deposition stages, where having homogenization temperature within the range of 108 to 220 degrees Celsius. So, now we see that this data were supplemented by extensive analysis of fluid inclusions of these different generations, these liquid vapor inclusions, the liquid vapor plus halite inclusions, or the liquid vapor and constituting or having more than one daughter crystals. So, synthesizing all the data, the authors they proposed 4 fluid components. So, these fluid components were essentially based on the chemical data. One of the major one of the very important chemical parameter for discriminating or distinguishing these fluid types was the bromine by chlorine molar ratio, and the fluid A, which is dissipate of the main ore fluid in the copper sulphide ores present in barite and fluorite. These have the salinity, moderate salinity, or rather low to moderate salinity of 10 % NaCl equivalent. This particular fluid came out to be rich in copper and uranium and have a very low bromine by chlorine molar ratio of 0.003. That is actually the characteristic which is assigned to a magmatic source. So, they deciphered that this fluid A is essentially is a magmatically sourced fluid, and their speculation was that this fluid is actually not by normally what happens in a granitic magma, the fluid which is exhaled from a crystallizing plutonic body. Rather, this is a fluid which actually was resulted from the degassing of the Gawler Range volcanics, and this degassed fluid subsequently got oxidized in contact with the atmosphere, and then it formed with kind of an acid volcanic lake environment, and that fluid later migrated through the oxidized aquifer and become the main stage ore fluid. So, here the distinction, even though this fluid is of low salinity and also lower temperature, the based on some of the key parameters like the molar bromine and chlorine ratio, it is ascribed to a magmatic source, but the magmatic source which is of a little different than what generally happens in normal mineralization associated with felsic magmatism. So, the fluid B was in the siderite and quartz. The salinity is high, represented by the liquid plus vapor plus halite inclusions, and they have low, and also along with this chlorine bromine to chlorine molar ratio, elemental species like potassium, rubidium, lead and cesium were also routinely analyzed by these workers in the inclusions of all the different stages, different types, and there were minor variations in the ratio also, and one of the ratio was important ratio was the calcium by sodium in the fluid. So, this particular fluid would have a very low calcium by sodium ratio, and as we go from fluid A to fluid B turned out to be a little higher in its calcium by sodium ratio and modest concentration of copper. So, this particular fluid was again inferred to be a reduced magmatic hydrothermal brine modified through interaction with rocks, but it remains uncertain whether this particular fluid is actually exhaled from the any of the younger granite member that we see in the deposit geology. And the fluid C is actually fluid is in the bornite fluorite barite association and mostly from the barite. Here the calcium by sodium ratio is higher compared to the fluid B, and also have a higher bromine by chlorine molar ratio, and which cannot be ascribed anymore to a magmatically sourced fluid. So, the option was that it could be thought of more close in characteristics to a basinal fluid, basinal brine with high copper and salinity within the range of 16 to 25 weight % equivalent, that is expected in kind of a cornet fluid or a basinal brine. And fluid D is actually in the fluorite in the lead veins cross cutting the brachiated zone. The salinity was of the range of 19 to 30 weight %, and these are possibly sourced from also from basinal brine based on their highest obtained calcium by sodium ratio. And so, these kind of fluid with their copper concentration which was also high were mostly have similar characteristics to what we see in case of the copper deposit in stratified sandstone like the Cooper Schiefer kind of fluid. So now, if we see here, then fluid A and B are essentially could be clubbed to one category of a magmatically derived fluid, and fluid C and D were more akin to can be clubbed together to be fluid which is derived from a basinal source. So what we see is that, and these authors also did ascribe the mechanism of the deposition to be coupled oxidation reduction of iron and deposition of the sulfides, but the same conclusion was arrived at with much more elaborate chemical data, in situ destructive chemical analysis like LA-ICP-MS analysis, and through which many of the important chemical parameters come out to help us in better identifying the source of the fluid and also the evolution, the way the fluid evolved. And in this context, it would be worthwhile that what is happening or what exactly some other important characteristic, with of course concluding our discussion on the application of fluid inclusion data to mineral deposit of hydrothermal over environment. This diagram, which is also taken from Wilkinson 2001, we could see is a nitrogen, helium and argon diagram, in which we see that there are some field, like this is field, the 1 is the field of magmatic fluid, 2 is the fluid of T2 is the field of Contd fluid, and 4 is the fluid of deep circulating mid-Vedic water, 5 is for rift basinal rhyolites, and then this A is for air, and the 3 is for shallow circulating mid-Vedic water, and this ASW is air saturated water. So if we have an analytical facility to actually extract the fluid or the gas released from the fluid inclusion cavity, and if we could analyze for these nitrogen, helium and argon, the fluid ancestry also could be ascribed to, and these also will help us a lot in addressing the issue of fluid origin and evolution. So now we will conclude our discussion on the application to mineral deposit environment, hydrothermal environment, by adding a little bit of idea on whether fluid inclusions or fluid inclusion microthermometry data or fluid inclusion microthermometry as such could be helpful in mineral exploration. Now, before we look into any of the 1 or 2 case studies or examples, we should keep it in mind that this is just another geochemical method, and any successful discovery does not come out of only a single method, and it is just it also involves a little bit of and as it happens in many of the practice of exploration, a success in one particular area cannot directly be extrapolated to another area, because these are very much specific to the kind of geology and many other essential constituent of the mineralizing system, and which these days we say is a kind of mineral system approach, but these can always be very successfully applied or could be tried as any other method. And since a successful discovery is always a combination of many techniques and many methods results put together, and so fluid inclusion technique will always can have a component which can add to successful delineation of ore bodies in different areas, and here this should be also more applicable to areas what we call as a where ore deposits are there or in a particular ore district, to augment or to discover some more such mineralized ore bodies in an existing ore district, which is basically known as the brownfield exploration. So, the problem is that this is not a very commonly adopted and practiced method. They may be sometimes because the lack of facilities or the lack of acquaintance or knowledge about, and also to have that much of belief in this particular technique that it will also help in exploration, but it is a cheap method, and if it is adopted, it will definitely give valuable information or valuable input for successful mineral exploration. This is just an example. So, while discussing fluid inclusions for mineral exploration, as Jim Wilkinson has put it, that it could either be that occurrence of any specific inclusion type that might indicate occurrence of a particular type of mineralization, or it could be a systematic variation in microthermometer compositional property which might indicate the direction in which particularly an ore body is occurring, or a ore bearing fluid could be more productive in space and time, or a specific situation such as a boiling and mixing, which we have seen in many cases that boiling is a very efficient mechanism for bringing about deposition of metals from fluid which is transporting the metals, and also the mixing trends like discussing the tin bearing granite pegmatite system in the Bastar craton. We also saw that a mixing, when it is identified, will always indicate staniferous pegmatite compared to a situation in which either of the fluid to be present. So, many of the situations can be taken into consideration while applying or attempting to apply fluid inclusions to mineral exploration. There is one example, this is from the Larafella mineral prospect from Burkina Faso in northwestern Africa. So, here this is a very quick and a small example, that this represent the black line, a black curve represents the gold grade in ppm, and this is ppb, let us say gold grade in ppb 2000, 6000, 10,000, and these are the points at which the depth at which the drill core has been logged in terms of the gold grade. So, this we can see, and these bars represent the abundance of aqueous carbon inclusion, carbon dioxide water bearing inclusion. So, what is observed here is that wherever there is a carbon dioxide bearing inclusion, it is immediately preceded by a high concentration of gold. So, this gives us an idea that in areas wherever we do the drilling, and without even before going to the determining the grade of gold by any elaborate method, one can quickly see the fluid inclusion characteristics and can find out or can conclude whether there would be a gold rich zone within the immediate vicinity or immediate, and sometimes also, as you have seen in case of the orogenic gold deposit, the methane concentration of the carbonic fluid is also a good indicator of gold rich zones. Those can also be very effectively utilized. So, the modern techniques of in situ destructive and non destructive methods like laser Raman, and which we will be discussing in the subsequent classes, and these have also come up to produce some quick data which would be useful in any kind of a mineral prospecting exercise. And this is an example from the famous McIntyre-Hollinger gold mine from the Timmins district of Abitibi province, Canada, which was way back in 1985 done by Smith et al. And this is a very interesting diagram where one can see, so these particular contours are based on the mole percent of CO2 on the inclusions, and we could see that the mineralized province actually is, or the rich mineralized zones are basically falling on the contour which is actually more than 5 a particular, say more than a particular value of the mole percent of carbon dioxide, which is 5%, 5 mole percent of carbon dioxide is coincides. So, these numbers which are shown here are the occurrence, the location of the mineralized bodies in this particular ore district. So, this is another good example of how the fluid inclusion characteristic would correlate with the rich mineralized zone. So, one last example, this is from the Sangdong Skarn deposit in China, where the mineralization occurs in form of the ore bodies which is shown as the hanging wall, the main ore body and the foot wall. There in the carbonate rocks, they are essentially the skarn type of mineralization, which is later on overprinted by veins containing molybdenite and the wolframite. So, the mineralization both is skarn and veins, and the scheelite both in scheelite in both the types, and the molybdenite wolframite in the vein type, and in any particular ore body, the ore body is exhibits a typical zoning from garnet wollastonite to pyroxene garnet to amphibole garnet to quartz biotite and quartz muscovite, with the tungsten percentage increasing. Especially it is shown this quartz muscovite zone is the central part and is surrounded by the quartz biotite, the amphibole quartz, and the garnet pyrite, pyroxene garnet, and the garnet wollastonite zones. It is essentially that there must have been a response to a intrusive felsic unit, which is somewhere in the at depth, which has given rise to this original or the primary skarn mineralization, which was later on overprinted by the vein type tungsten mineralization. So, quickly if we could see that while doing the fluid inclusion work, the microthermometric data which were taken on pyroxene and garnet and also quartz from all the zones of mineralization, and a contouring of the fluid inclusion temperature has been done here, like shown here. The high temperature zones, like shown here, generally coincide with the highest grade of the ore in terms of the highest tungsten grade. So, while doing so, it was observed that there is another kind of a zone which also showing a high temperature characteristic of the ore fluid. So, it is certainly very empirical, but then on further exploration and drilling, it gave rise to a new skarn ore body which is very near to, or which was earlier unknown to be existing, and which could only be brought out by systematically looking at the fluid inclusion microthermometric data and their presentation in the form of contours. This is also another interesting example as to how it was done. So, to conclude, I would again also include in the discussion about one interesting kind of methodology which is also used for mineral exploration, which is being done by Kingsley Burlinson, who is having his own Burlinson Geochemical Services, Darwin. So, what he exactly does is he uses the decrepitation of the samples and put them into a furnace, and then using some amplification of the sound that is generated with which is very much computerized, generates this kind of graphs, with these graphs which is shown as a temperature versus counts per 10-degree interval. So, these peaks essentially indicate the temperature at which there is majority of the inclusions which decrepitate or burst because of increasing temperature. And as you all know that from the very fundamental idea that we had about the fluid inclusion types, that the aqueous carbonic inclusion generally when they are heated up, because of the building up of high internal pressure exceeding the yield strength of the host mineral, they decrepitate or they burst, and during the decrepitation whatever sound that is produced because of this decrepitation, this is amplified and recorded in something which is called a decrepitogram, and this is extensively used, or this can be used and correlated with the, like as has been shown before, like the in terms of the gold grade and having a correlation of the decrepitation peak. So, which are the samples where, depending on where the decrepitogram peak is obtained, some delineation of the ore body or the rich mineralization zone could be delineated, as is being practiced by this method. For further consultation on this particular methodology and many other examples that he cites, that on many deposits across the world which Kingsley studies for this decrepitation behavior and presents them in the form of a decrepitogram here, can be consulted from this link that is provided here. So, we conclude our discussion on the application of fluid inclusion microthermometry to ore forming environment, and as I have said that the original literature that will be cited necessarily have to be consulted for a better and greater detailed idea about what has been proposed here, and essentially it is just to get the trick of the trade, that how the fluid inclusion types, their entrapment in different host minerals, linking them to the different stages of the mineralization have to be very judiciously established. The inclusions have to be studied from different hosts, and then such kind of synthesis of the information can be made to understand the origin and evolution of ore fluid in any mineralizing system, and also to apply them to useful outcome like mineral exploration. Thank you.